GPS signals. I know I have way too many slides, so I'm going to blow through a few. This is what the 5-year footprint looks like. Ignore the fact that it looks like Jar Jar Binks' tank. But we had the overall 5-year footprint, deep drilling fields in the supernova fields, the science verification area, and we are now, because we're so efficient, we are now starting the 6th year of a 5-year survey, or something like that. We're using 5 filters, the DES, GRIZ, and capital Y filter. The GRI filters are very similar to the SDSS filters. The Z filter, the Z filter for the Brits in the crowd, the Z filter, we've put a red edge on, so it's actually a filter-defined band now. And the Y filter is different than all the other Y filters in use, just because. The goals of the survey requirement for photometric calibration is a 2% RMS over those scales, 1% over the entire field. This is really difficult. When I was a grad student, I said, piece of cake, right? Absolute color, we need 0.5% color in, or 0.5% absolute color in G and R, R minus I minus Z, and 1% at Z minus Y. This is incredibly difficult to do because there are no good Y standards. And these are used by the angular clustering group, the PhotoZ group, the supernova group, and the absolute flux, we need 0.5% in the I band relative to, things shifted again, BD plus 174708, until Ralph Bolin and Arlo Landolt said, it's a variable star. And so we switched to C26202, which is one of the CalSpec standards. And we've also done follow-up work on BD plus 174708. The paper is coming out, and no, it's not a variable. This is the overall target of what our calibration survey looks like, system looks like, with all this stuff going on mostly a nightly survey, and the white dwarfs fit in here in the global absolute calibration. They are used to set the 0 point for each of the filters. So this is our rough plan, and this is all the Y1 data. Y2 has been released. Y3 is getting ready to go public soon, I think. I don't do the survey stuff. We're into processing Y4. And so I will show you some results we have. One result we have with the Y1 data with respect to Gaia. And we have internally Y3 with respect to Gaia 2. We have shared that with the DR2 folks. And we're going to be having a meeting because they've got an error in their photometry. I don't think that comes as a surprise to the Gaia folks. Does it, Martin? Okay. So initially we set up a bunch of tertiary standard stars in the field. The green that looks like the Exxon Valdez after it hit the reef was a result of the what we did the pre-cam survey using the Curtis Schmidt telescope, where we covered those RA deck lines 10 times plus each in each of the 5 filters. That was an interesting experiment also. The survey itself, we tile multiple tiles, 10 tilings on each part of the sky. Each one will be in a different part of the focal plane, so that we try to remove the survey or the CCD effects. Whoop. Go that way. So this is the year 1 data compared to forget which one this was compared to, but we get fairly good survey, and you notice the survey year 1, year 2, we came back and filled in the missing pieces, and then we've been covering the sky since then. But we were down to 3 millimegs across the sky at the R band on average because of the survey we're doing. And this is part of the PGCM, which is one of the photometric global calibration systems that we use before the absolute. We find we can do really good internal accuracy comparing across the field of view. It's tying that to the external references is where the problem is. So the general idea is we fit a DA white dwarf that is not variable, hopefully. We do synthetic photometry using the spectra of the white dwarf, and then we can tag the zero or the derived magnitudes to pin what the white dwarf should be in each filter. And the preliminary survey, like I say, the preliminary data were against C26202. We're using a sample of about 30 to 100. We're up to about 50-ish really well characterized ones now. We've got about 200 DAs in the pipeline. And these are scattered around the sky or around the footprint, so they all have to meet. This is an old plot, but this shows some of the initial coverage. The basic samples, a representative sample just of the various DAs. Pierre Emmanuel has done most of the modeling for us, and he gets good fits because Pierre knows what he's doing. Not sure the rest of us do, but he does. So we believe everything he does. Right? Oh. So just a representative fit using SOAR 4-meter data that Pierre Emmanuel did for us. Again, we get good data. We also went out and found, working with Abi Saha and Jay Holberg's group with the HST experiment to produce really high precision DAs from space using HST. Gautam Narayan, who's at Space Telescope, has also been working and modeling our data, and we find, don't have him model cool white dwarfs because his code does not work for cool ones. Pierre Emmanuel's does. That's the plug. But you notice the observations, the fits are pretty close. They're like within 1% of each other or less. So the goal, one of the questions we have is interstellar reddening. We'll be starting to explore that, especially with the Gaia data. All these are fairly nearby white dwarfs though. And unfortunately, Deborah Gullidge is one of my former undergraduates, now in between grad school, and as all undergraduates are, when they become useful, they graduate and leave. So I now have to train another one. Initial results versus C26202. So what we have so far, we did 25 objects. I know it says 154 objects. That actually is a 154. There's a my computer puts weird things in. 154 objects with the 1.5 meter that Deborah reduced, not realizing only 25 of them were actually targeted as white dwarfs. The others were targeted as standard stars for other things. They're generally too bright to use for the actual DES calibration, but they make a great undergraduate training set. And she's found some interesting results, and I've got a poster up in the room with some of the 1.5 meter data and some of the Apache 0.3 meter data. The actual results we have from SOAR, APO, the AAT, and Magellan. So for SOAR, we pick our targets from Supercosmos and the Atlas surveys. 145 that we've targeted so far. We have another 8 nights of time coming up this semester. 111 of them are DAs, 12 DBs, 2 magnetics, and 20 others, whatever an other is. APO, we've gotten 83 targets, roughly 75% are DAs, 2 quasars, which make great undergraduate papers, 1 CV, which Assassin then found a 1.5 years later after it went boom, a handful of DBs and others. The Anglo-Australia telescope, we've got 32 spectra obtained, and we're still waiting for those reductions to come in. And Magellan, we have 12 so far. 11 of those 12, which were color selected, are DAs. We've got 18 more in the can, and we're waiting on the 2018 time to come up. The imaging follow-up, we're using primarily the 0.9 meter at Cerro and at Kitt Peak, and we're using that to get the U-band photometry because DES does not include the U filter nominally, and we can't convince them to give us nights to do that directly. And we're also monitoring some of the candidates for signs of variability. We have some that we found that are in the variable range, not pulsators, but variables. So I can't give a talk without having a cat. This was the only cat I had on my laptop. So this is your standard 12-meter cat. Up. He's supposed to disappear and disappear. Anyway, the conclusion are we're in work. Papers will be coming out here shortly, and this will be available to the community through the DES, but also not through the DES because it's not an official DES project to tie it to an absolute flux scale. And for LSST, all of this will potentially bootstrap straight to LSST. Oh, no. Oh, now you have to wake up because you have real speakers coming.
Okay, so our next speaker is Kevin Bird. He will talk about the systematic search for compact Dwarf binaries.
This is so YouTube can pick you up.
All right, cool. All right, so my name is Kevin Burge. I'm a graduate student at Caltech working with Tom Prince. I've also been working very closely with Thomas Kupfer, who's here in the audience. And my interest is primarily in LISA science, looking for gravitational wave sources that LISA will be able to detect. And so what I'm going to be talking about are finding compact white dwarf binaries in the optical time domain. And so just to highlight the time domain, there are a lot of surveys, both existing and new surveys coming that contain a time domain component. I work primarily with ZTF and PTF, which are dedicated time domain surveys, but I want to emphasize we've heard a lot about Gaia, which provided us with key pieces of information like the parallax in DR2, but those also come with a time domain component. And the other thing I want to mention is that the galactic plane is being included in more and more of these surveys, and this is something exciting if you're interested in stellar science in general. And I just want to show a comparison of some of the detector areas of modern surveys. And so one thing you probably notice is ZTF is huge. But one thing I want to emphasize is that DES and LSST go much deeper than ZTF. And so they will detect far more sources. But I think one of the strengths about surveys that go to the depth of ZTF is that if you're working with LSST data, sure, you may find a lot of interesting things. But unless you have time on the 30-meter telescope, getting phasors off spectroscopic follow-up is going to be difficult. ZTF, on the other hand, is very well matched to the spectroscopic resources we have. And so one thing I want to mention is ZTF is going to be doing a high cadence survey of much of the galactic plane. And if you want to hear more about that, stick around for Tomas's talk later. So I just want to briefly say, the way you find white dwarf binaries, well, one way of doing it in the optical time domain is you look for periodic modulation in their light curves. And a survey like ZTF has a strength in finding these because it accumulates a lot of epochs across the sky very quickly because of its detector area. And so what you do, the three physical effects that can give you these periodic modulations in general are eclipses when one companion occults the other, which you can see in this light curve, which is of J0651, the 12.75-minute binary discovered by Brown et al. Ellipsoidal modulation, when you have one component tidally deforming the other, which you also see in this light curve. It gives you a modulation at twice the orbital frequency. And then finally, if you have a binary where one companion is much hotter than the other, you can also get a modulation on the orbital frequency. And I just want to show this. This is actually a ZTF light curve of that same binary. No, it does not look as nice as the publication quality light curve. But I wanted to show this because we actually did a test run of ZTF very early in commissioning looking at that field. I period searched the entire field and managed to blindly recover this object as the most significant object with a period between 10 and 20 minutes. So it's a proof of concept that you can pick out something like this using just time domain data. And so one of the challenges I've encountered in doing this, though, is if you want to search to very short periods in long baseline data, the frequency grid you have to search is enormous. And so one workaround I found is using GPUs, graphics processing units, one's pictured here, which are very good at doing relatively simple computations massively in parallel, which is period finding in a lot of cases. And then finally, another challenge that has recently come up, thinking about J0651 and similar systems, is that systems where the orbital period is changing, that can make it difficult to find the periodicity in long baseline data because the features drift in phase. But I want to get to results to keep everyone awake after lunch. So when I first started working on PTF data, which is about 1.5 years ago, I went looking for post-common envelope binaries in PTF with period searches. And so I found 50-something new candidates, which they're in a paper that's being worked on, about half white dwarfs, half subdwarfs. And so some of the interesting systems that came out of that search is the shortest period known HW-Ver system, which is a subdwarf being eclipsed by a main sequence star or a brown dwarf, in this case a brown dwarf. This isn't that much shorter than the next shortest, which is 96 minutes. This is maybe more exciting to more people. The shortest period pre-cataclysmic variable, and we're saying it's a pre-cataclysmic variable because it doesn't show signs of accretion. This is at 63.7 minutes. This isn't an eclipse, this was a cloud, so just to let you know, don't get too excited. And then finally, in a separate search, I found 3 new white dwarf subdwarf binaries where the subdwarf is being tidally deformed by the white dwarf. And Tomas has done some really interesting work in following these up, and I would really encourage you to come to his talk later to hear more about them. But moving on to the more exciting things, I said I was interested in LISA science, and I actually found one candidate in PTF for a LISA source. And so this is a little bit to digest. Let me walk you through this plot. The blue curve is the RV curve as taken with LRIS on Keck. The orange curve is the light curve taken with the high-speed photometer Chimera on the 200-inch. And what you're seeing is ellipsoidal modulation in the light curve that is phasing up as expected with the radial velocities. In fact, it's hard to see in this plot, but there's actually some Doppler boosting that coincides with the maximum blue shift exactly as you would expect. And so what I hope has gotten your attention by now is the scale. It's quite large because the thing is moving quite fast. And the reason for this is it's a 20-minute orbital period binary. And I say proof of concept here because I believe this is the first gravitational wave source ever isolated in a large-scale survey purely based on its optical time domain periodicity. So it's a demonstration that we can pick these things out using their periodicity. It's also exciting because its atmosphere is full of helium lines, but it also has some hydrogen lines. And so Pierre-Emmanuel and his student Elena have actually done the modeling for this because we had no idea how to deal with this. And anyone in the extremely low mass white dwarf community probably recognizes that there aren't really any systems out there like this. So this system is exciting, but before the end of my talk, I also want to get around to some ZTF results, which I hadn't anticipated even presenting at this because I didn't get the data until early June. So the survey started in late March. And I remember I got my first batch of data. Well, I was told it was ready on a Wednesday in early June. It took me 2 days to download because it's a massive data set. But by that Friday, I had downloaded it, and I did a global period search across every object in it. I want to emphasize the only selection criteria I put on was some minimum number of detections. No color selections, no Gaia selections. I searched everything. And so in that, I found some interesting candidates that we then triggered the EMCCD on the KIP-Peak 84-inch that's recently been mounted on it for rapid photometric follow-up, which has been a very useful tool in doing this kind of follow-up. And so I had my first candidate Sunday morning because the period search finished Saturday night. It took about 2 days, so the GPUs are fast. And out of it is one candidate was a nice new eclipsing system that we confirmed on the KIP-Peak 84-inch, which was very exciting. ZTF is already doing what we wanted it to do. And we further followed it up on Chimera on the 200-inch, and we saw that not only is there a primary eclipse, there's actually a secondary eclipse. It's very subtle, though. And so this thing is even more exciting, though, because we further followed it up on Keck and found that it's a double-lined eclipsing binary, which if you work on binaries, you know there's not much more you can ask for. And so now I want to put this all in the context of LISA science. So this is from Tomas's recent paper where he basically calculated the updated characteristic strains of the known LISA sources using Gaia information. And so just for reference, this is the LISA sensitivity curve after some number of years of integration. And this is the characteristic strain of the sources after those number of years. And so what you see here is HM Cancri, the 5.4-minute binary. V407 Vol, the 9.5-minute. These are both periodic X-ray sources. That's how they were detected. They're both thought to be direct impact accretors. And then J0651, the 12.75-minute system, which is exciting because it's the only eclipsing system on this diagram. And so we've calculated the expected strain for the 20-minute binary, and it falls about here, which is exciting. It's detectable. And another reason that it's really exciting is it's a single line binary, which makes it tough to put constraints on some of the component masses, but you can actually do O minus C to measure the P dot from the ellipsoidal modulation. And if you're willing to assume GR is governing the orbital evolution, that actually gives you an extra constraint. It's an extra measurement. But the other exciting thing is that light curve I just showed you of the eclipsing binary is also on this plot, and it falls here. And I'm sure that got some of your attention. And the reason it should is it goes between HM Cancri and V407 Volt. That's because it has a 7-minute orbital period. And it's quite exciting because it's also doubled the number of eclipsing systems on this diagram. And so I want to conclude by saying there are a lot of people who've contributed to the science of this. And this is actually a movie taken with the KitPeak 84-inch EMCCD. In real life, you have to wait a long 7 minutes for this to happen. So this thing's almost completed 2 orbits in this talk. But I want to say my concluding note about this is I think the time domain, the optical time domain is proving that it's a very powerful tool in picking out interesting systems. And just based on the speed with which we recovered this in just the first 2 months of ZTF operating, we either got really lucky or I'm expecting a lot more of these to appear in the next couple of years. Thank you.
For questions. Alan, please come up. So now it's a joint question and answer session. So,
I was wondering if there's any. Yes.
You have threads and houses.
Hello.
You can use this one too.
Yeah, sure. Make it come to me. Yeah. I was just wondering if there's any evidence of current accretion, or is it, has it started to overflow torch lobe? Like, what can you tell us about that boundary?
I can tell you it's ambiguous. There's some evidence that suggests it. I would say there's more that suggests it hasn't. And all I can say beyond that is wait for the paper at the end of this year when we'll get more data and have a more definitive answer on that.
And from the light curve modeling, can you get masses? Like, is there Doppler beaming? That must be great.
We haven't actually measured it yet, but yes, we would expect there to be some Doppler beaming. But like I say, we still need to get a lot more data on the system. Just discovered it 6 weeks ago, and we only have so many telescope nights.
Now we all know about it. So.
Yeah, good luck. Good luck at finding it.
I can just talk about it. And Kevin, is there a possibility if you find too many of these that it becomes a noise floor and that becomes a problem for GW detection, or because they're monoperiodic?
That's a good question. It's possible that you might start building up, the noise floor might in fact be higher than we expect, but you would still expect the strongest sources to poke out of that noise floor, right? So I think this is one of the reasons the science is so interesting. LISA's coming online in more than a decade from now, but we still have so few examples of these. We need to learn a little more about them.
go ahead. Yeah.
Yeah, I can run.
Oh. I can do it.
Shouting is like. Me. I don't know if you mentioned this, so I came in a little bit late, but do you know what kind of time it takes for the system to actually merge?
Very roughly order 100,000 years, but that's still a very rough number.
Okay, so keep me on it.
Any question on the dark energy survey?
You don't have to, but.
Yeah, actually, I did. It's a little broad question. You mentioned that you have like 500 candidates for variables. These are pulsating?
No,
Finally.
we have observed 500 white dwarfs as potential calibrators.
Oh, sorry.
So far, only about 2, we've only confirmed 2 as variables, but there have to be more in the system. We have some magnetics. I've got a poster up that has a couple of magnetics. They're variable by definition.
And then the observations, separation between the observations, do you think that it will be possible to search for candidates for pulsating stars?
From the work I'm doing, no, because we observe usually for a week, or so once or twice a year. In the survey itself, I don't believe we will, because we only get 10 shots spread over 5 years on each field. The LSST will be the place you'll start finding
That was a
pulsators.
very, very large thing. Okay.
We have time for any additional questions? Okay, if not, let's thank all our speakers.
That was like what?
All right, so we'll move on to the next section. It's on why you won't as hydrolyzation silver progenitors. The first speaker is Stefan Gaia, who will talk about progenitors and the projected companions of thermonuclear supernova, the Gaia has.
Hello, everyone. First, I thought it's a good idea to get a talk on the Monday afternoon because I'm done afterwards. But now, after Kevin's talk, this is a very tough slot to impress you. So the first thing I did, I changed the title of my talk a little bit. So I will concentrate on the ejected companion part, and Thomas Kupfer will cover the progenitors. So that gives me a little bit more time to cover this topic here. So start with the concept of the hypervelocity star. So since about 13 years now, a couple of stars are known that are so fast with respect to our galaxy that they exceed the escape speed of the galaxy. So they are actually ejected out of the galaxy, and most stars don't do that. And it's also not so easy, so there must be an acceleration, one or more acceleration mechanisms for that. So how did I enter this game? By chance, because actually the second hypervelocity star that was discovered was actually this one here, US 708. And we did some follow-up of this object. We took spectra with Keck, and we actually, to tell you that it sounds a little bit weird, we used ground-based probe motions and did that by hand. So Eva Ziegerer, our PhD student, also used photographic plates. So in the Gaia era, that's something. Yeah. So the star has a very high radial velocity, as you can see. And the other thing that you can see is that this star has a very strange composition. You see here only helium-2 lines that are seriously Doppler shifted with respect to the rest wavelength here. So what you can see is this star is very, very fast. And if we put all this together, we end up with a galactic rest frame velocity of about 1,200 kilometers per second. That's about twice the local escape velocity from the galaxy. And this star turned out to be the fastest unbound star in the galaxy. And if you look at the plot there, you see the possible origins of those stars in the galactic disk. And you see the galactic center is not included in this possible origins, and that's where usually people thought the hypervelocity stars should come from, being disrupted binaries, disrupted by the supermassive black hole in the center of the galaxy. So what has that all to do with white dwarfs? Coming to that. The interesting thing about this star is it's in comparison with all the other known hypervelocity stars, it's not a main sequence star, it's a hot subdwarf. And as most people in the room should know, hot subdwarfs like white dwarfs. So hot subdwarfs are cores of red giants that are formed, or most of them are formed by binary interactions. And one of those interactions is common envelope ejection. And if you look at hot subdwarf stars, if you observe them spectroscopically, lots of them are indeed in close binaries, and as companions, they like white dwarfs most. So we have a lot of close white dwarf subdwarf companions, and this guy here sticks out. This is actually CD-30. I think Thomas will talk about this a little bit more later on. This is a very compact binary star, as you can see. Of course, not as compact as Kevin's, but still 1 hour. And it has a rather massive white dwarf companion. And when we prepared this paper together with our theory friends from China, we found out that this binary is so close that it will get into contact during its evolution while the hot subdwarf is still a hot subdwarf. It didn't evolve. It will not evolve to become a white dwarf. Okay. Yeah. So, and the parameters of this system fit very well to a so-called double detonation thermonuclear supernova scenario. And now we are at the point here. So, as soon as the hot subdwarf fills its Roche lobe, it transfers helium material on top of the massive white dwarf, and this may lead to the detonation of the helium on the surface of the CO white dwarf, and this in turn might trigger the CO fusion in the core, making causing a supernova type 1a. So in principle, the reason why the star is a hypervelocity star is the white dwarf, the explosion of the white dwarf that kicks out the star out of a very tight binary system. Okay. And yeah, we got a nice science paper about that in 2015. And of course, if you find such an interesting object, you want to find more of them. And what I did to find them is put together a whole catalog of all known hot subdwarf stars and try to get as many information about them as possible. I now have 1,900 STOPs with atmospheric parameters, radial velocities, spectroscopic distances. And in the pre-Gaia era, in the last couple of years, I used ground-based probe motions to have a list of objects to follow up, of candidate high-velocity objects. We published 5 fast STOP stars during this time. And we did a quite massive spectroscopic follow-up because you need the spectroscopic distances for those stars. They are even too far away for Gaia. You need the radial velocities, and yeah, so we used a lot of 4 meter and also 8 meter time to prepare this list. And this is the distribution I showed in Warwick 2 years ago. You can see the galactic rest frame velocity, and you can see the boundary between bound and unbound. This is a rough number here. So everything higher than 600 kilometers per second could be unbound. So that was the sketch in the past, in the pre-Gaia era. And of course, I've waited years and years until Gaia will come. And the very first thing I did when Gaia came here was checking US 708. Still there, still not coming from the galactic center. Still fast, a little bit less fast now. These are different assumptions for the spectroscopic distance for different scenarios. Everything looks pretty similar. We now have about 1,000 kilometers per second galactic rest frame velocity. All fine. What happened to my candidates? This is the distribution from 2016, and this is the new one. So you see, lots of objects remain. So they are not all outliers from the ground-based probe motion surveys, but most of my subdwarfs are now bound, which is actually a healthy thing, because subdwarf stars are thought to be to originate from solar-type stars, so they can be very old. And those guys are just very, very, very extreme halo stars. They are born and raised in the halo on very extreme orbits, going out a few more than 100 kiloparsecs away from the disk and back. Okay, and then we still have these 2 guys here next to US 708. Where I got Keck spectra from Thomas two or 3 weeks ago, and well, those Keck spectra indicate that they might also not be real. That's it's not the end yet, but still. So well, and then you are in a situation you think you are quite well prepared, and it should be possible to find yet another star. But then, but still, you see me smiling, and that's not frustration. I'm still happy because I say it with a very known German philosopher. Nach dem Spiel ist vor dem Spiel, which means after the match is before the next one. And Gaia now really kicks ass, yeah? We can really do a much better search for those high velocity stars. I put together a complete Gaia all-star catalog with help from Roberto and Nicola. Thanks. We have now 40,000 SDOP candidates, and where we can do the search again and better. And well, my preliminary numbers might be a little bit too optimistic, but I haven't given up. Yeah. So, okay. There might be a connection to the other weird objects I think Ken will show later on, the hyper white dwarf stars. And that might be one reason why we did not find more US 708s, but I think Ken will talk about that in more detail later. So what are we doing in the future? We want to look for progenitors and ejected companions. We put a lot of subdwarfs in the target list for tests to get light curves. That's very well suited to look for close binary subdwarf white dwarf systems. Then I became a member of the BlackGem consortium, where we get multi-band ground-based light curves. Also very interesting for this type of kind of research. And of course, we need spectra. And we already heard about the projects to observe white dwarfs. I want to do the same with subdwarfs. And for this, I'm starting negotiations, and I will enter the foremost collaboration to get as many objects in the target list as possible. And to talk about these fast stars, I invite you all to my new institute, where I just started 1st of April next year in August, before we all go to Hawaii, to join us at the Stars on the Run 2 conference. It's about all kinds of stars that are too fast to be normal. Okay, so finally, a little bit of advertisement. This is my new location in Potsdam, where I started a new group. This is my group, my 3 postdocs. One is here. It's a nice place. If you are around, tell me, I can invite you. And another thing, if you want to work with us, there is an opportunity now. There are 2 junior professorships advertised now in the University of Potsdam, tenure-track positions, and one specifically for theorists working on compact objects in relation to gravitational wave sources. So to all of the young people here, theorists, compact objects, apply, and it would be great to have someone to work with in the future. So thank you very much.
Our next speaker is Ken Chen, who will tell us about confirming the 86 type of one-day supernova scenario with hypervelocity white dwarfs in Gaia VR2.
What do I do pointing with? Ah, okay. Yeah, so today I want to tell you today about how the scenario for type 1a supernova progenitors that we've been working on, how I think we've confirmed that it actually does happen and does lead to type 1a supernovae using Gaia Data Release 2. Now, another title for this talk could have been, do dynamically driven, double degenerate, double detonations direct dwarf death? Does this scenario, this D6 scenario, actually cause type 1a supernovae? And I think the answer is definitely. I want to try to convince you of that. This list here, how do I do the pointing? What's that? This list here is some of the other authors on this paper who are in the audience right now, and I just put that there to remind them to come up to me this week and find me because I owe you all beer. Okay. So there's not a whole lot of time in this talk, but I do feel like I do need to motivate the historical progenitor scenarios for type 1a supernovae very, very rapidly. So we all know, I think, that carbon oxygen white dwarfs, exploding carbon oxygen white dwarfs are what lead to type 1a supernovae. But obviously, white dwarfs are very stable on their own. We need something to cause them to explode. And so the name of the game in the 1A community has been to figure out what triggers the white dwarf. What is the binary companion that causes the carbon oxygen white dwarf to explode? Historically, we've always discussed 3 main scenarios, something called the single degenerate scenario, where there's accretion from a non-degenerate hydrogen-rich star, builds the white dwarf up to the change of Sekar mass, and maybe it explodes. Okay, people also refer to what's called a double degenerate scenario, where it's two white dwarfs merging that increase the mass above the Chandrasekhar mass, and then maybe explodes. And a little less known, but also one of the main scenarios historically has been the double detonation scenario, which Stefan just mentioned, where there's helium-rich accretion causes a helium detonation that triggers a carbon detonation. But I actually don't want us to remember these things because I think they're actually very confusing because these names sort of hide a lot of the physics that's going on, and different scenarios get pushed into different groupings that they don't actually belong to. And the reason is because these names conflate the progenitor, the other companion, with how the explosion actually happens. Okay. And so this table tries to make that a little clearer, although I don't have time to talk about the whole thing right now. What it's trying to do is separating what the companion is and how mass is transferred from how the explosion actually happens. And the reason I'm trying to do that is because things like the single degenerate scenario that we talk about, where it's Chandrasekhar mass explosion from an accretions from a hydrogen-rich star, you can also have what's called a single degenerate scenario, the same explosion mechanism with a non-degenerate star, but it's an entirely different composition of stuff that's being accreted, for example. Okay. What I want to talk about the rest of the talk, though, is these two boxes here, where it's a double detonation scenario. That's how it explodes. But the thing that's the companion star is another white dwarf. And not only is it another white dwarf, it's another white dwarf where the mass is being transferred unstably. Okay, so it's a dynamically driven mass transfer. That's a dynamically driven part. It's two white dwarfs. It's a double degenerate scenario. But the explosion mechanism is a double detonation scenario. Okay, so it's a dynamically driven, double degenerate, double detonation. Before I go too much further, in case you're not a 1A aficionado, you might not know, maybe this is the first time you've heard of what a double detonation is. So I just wanted to show a simulation that has a double detonation in it. Okay, so this was done by Mikhail Fink 11 years ago now. What we're going to see is a helium-rich layer on top of a carbon-oxygen core. The helium-rich layer undergoes a helium detonation that sweeps around. And as it goes around, it's going to send a shockwave into the core that ignites a carbon detonation. So two detonations. So let's see that go. Right, so there's the shock wave that's being sent into the core, and as it converges, it sets off a carbon detonation. Okay, so that's the double detonation scenario. Now the simulation actually ends just as the carbon detonation gets going, so that's a little too bad, but we are currently wrapping up some work where we did our own double detonation scenarios. This is work with Dean Townsley that we're writing up right now. It's the same, you're just going to basically see the exact same thing. Helium shell detonation going around, it sends a shock wave into the carbon oxygen core, but for whatever reason, the color scheme isn't quite as good, and so you can't see the shock wave happen. But it is going in there, I assure you. What's nice about this, though, is that we continue to run it out so you can see the carbon detonation actually happen and go through the star. Okay, so that's a double detonation scenario. Now, again, this is we're focusing on a variant of the scenario where it's another white dwarf donor, and the mass transfer is unstable. Okay, and this is actually first pointed out in 2010 by James Guillauchon in a flash simulation. The main point is that as the mass is being transferred unstably, you get the stochastic generation of very hot little pockets in that helium-rich material, and those stochastically generated hotspots can lead to a helium detonation that then triggers the carbon detonation. There's a whole host of reasons why this scenario is really nice that I don't have time to talk about. I just left the text up there in case you want to look at the slide later to look up some of these references, but there's lots of nice problems that it solves in the 1A literature. The main point of the talk, the main point of the scenario for this talk, though, is the possibility that the scenario leaves a smoking gun in the form of a surviving white dwarf donor. Okay, and the point is that because the double detonation happens during the merger, it's possible that it happens so early in the merger that this white dwarf donor isn't fully merged. It's not fully disrupted yet. It's still intact. So this primary white dwarf might explode because of the double detonation, but this white dwarf donor might survive. And if it survives, it's going to be going off with whatever orbital velocity it had, which is actually very, very high because it's a double white dwarf system. It's very compact. So this plot shows the orbital velocities of various companions at the moment of Roche loop overflow versus companion mass. So non-degenerate stars are down here. They can get up to maybe a few hundred kilometers a second, just again because they're much, much larger. They overflow the Roche lobes at larger separations. Double white dwarf binaries, the white dwarf donors, are much more compact, and so you can get up to velocities between 1,000 and a few thousand kilometers a second. And so we decided, we're going to look in Gaia, and these should stick out like a sore thumb because these should be the fastest stars that show up in Gaia. So indeed, we went into Gaia and found the fastest stars we could find. We found 3 extremely exciting candidates. What we're showing here is the posterior probabilities of their total galactocentric velocities. As we heard in the beginning of this morning, you can't just invert the parallaxes to get distances because there are parallax uncertainties. And so you have to do some sort of Bayesian statistics to get posterior probabilities for things like the distance and the total velocity. That's what I'm showing here. As you can see, the total velocities for these three candidates range from 1,000 to a few thousand kilometers a second. So this is precisely what we expect for double white dwarf systems where the white dwarf donor survives. One thing I should point out, though, is that the radial velocity of one of these stars is sort of expected. It's 1,200 kilometers a second. This is D61, so it's the green line here. So its radial velocity sort of matches up with its tangential velocity, which is a few thousand kilometers a second. However, these other two stars have radial velocities that are consistent with being under 100 kilometers a second. So this is extremely weird. It's also quite worrying, right? We might just be picking out the weird stars that have bad parallaxes or something like that. And so maybe their total velocities are actually wrong. But for some other reasons that I'm going to get into, we think that the velocities are correct. It's just for some reason, these radial velocities are really low. And somehow we got extremely lucky or unlucky and found very strange velocity stars. So this remains one of the worries of this stuff, but I hope I'll convince you that the velocities are indeed real. Right, so with the orbital velocity information, the 6-dimensional information from Gaia, and plus the radial velocity, we can track back where these stars came from. This is one example. This is showing a top-down view of the Milky Way and a side view. The blue is the past history. And similar to what Stefan just showed, for these stars, they don't pass through the galactic center. And that was the common, or one of the most common ways you can get hypervelocity stars is with three-body interactions with the supermassive black hole at the galactic center. These stars don't come near the galactic center. They also don't come from the other galaxies nearby. And so these are really not being ejected via interactions with the supermassive black hole. They're being ejected from some other mechanism. So that's the velocity information. What do these stars actually look like? So this is a CMD showing the main sequence, the giant branch, the white dwarf cooling track. The subdwarfs are here. The regular subdwarfs are here. The three D6 stars are these three circles here. Okay, so again, we just picked these stars based on their velocities. We did no color cuts. We did no real cuts on them at all. They happen to sit very, very near each other in this weird part of the CMD where there are supposed to be no stars, right? There aren't supposed to, 3 minutes. There aren't supposed to be any stars there, and yet these three stars are all right there together. So they look very, very similar in colors. This star here, this diamond, is GD492, which Roberto will talk about. I won't mention it because I'm running out of time. Stefan just talked about US 708, which is over here, which also possibly has a connection to these stars. But again, I don't have time to get into it. You also notice these aren't white dwarfs, right? The white dwarf cooling track is here, whereas these stars are up here. The idea we have is that the supernova happened so close to them, it injected a lot of energy into them. And perhaps that was enough to puff them up, puff up their radii so that they appear there. But that's the subject of ongoing work, and it'd be nice to actually confirm that with modeling. Right, so like their CMD positions, which are similar to each other and unique from basically all other stars, the spectra of these three stars, which is shown in black here, is also, they're very similar to each other and also very unique from all other stars. DA and DB white dwarfs are up here. It's very obvious these are not DA and DB white dwarfs. They show some similarities to some peculiar white dwarfs, some carbon, oxygen, magnesium strong other white dwarfs, but they don't actually look exactly like them. The main things we can say are there's no hydrogen, there's no helium that's seen. They show strong carbon, oxygen, magnesium, calcium, things that we expect for the previous donors to type 1a supernova systems. And finally, I think the thing that really nails puts a nail in the coffin is that one of these stars comes from a supernova remnant. So a few days after we submitted it to archive, some people on the team decided, well, maybe we should see if one of them comes from a supernova remnant. And indeed, this blue trajectory takes it back into a previously known supernova remnant that has a consistent age. So the estimated age from this paper in 2015 was of order 10 to the 5 years. Take this back 10 to the 5 years, it puts it right here. The distance, it's also actually quite uncertain. It's 1 or 2 kiloparsecs, but it's also exactly consistent with this star. Oh, right. And Stefan Jordan sent me this video, which shows the trajectory of D62 in his nice program Gaia Sky, and it puts it into this circle, which is right here.
Backwards in time.
Yes, absolutely, backwards in time. I should also mention this is the only one of these stars. This is the only one of the stars that actually has high resolution H-alpha imaging that we can actually perform this search. So it could be the case that these other two stars also come from supernova remnants. We just don't have the data to look for them yet. So we're currently in the process of getting that. But I hope this convinces you that this is indeed coming from a supernova. I also should mention this is the farthest supernova remnant from the plane, which suggests that it's from a very old population, which suggests it's a type 1a supernova. Right, so I hope I've convinced you that we have found, I think, the first known detections of surviving companions to type 1a supernovae, and that we really have answered the question, does the D6 scenario work? And it actually does. I feel fairly confident that we have really convincingly shown that this scenario actually does produce type 1a supernovae. As I said, these three stars were picked only for their tangential velocity, and they ended up looking very, very similar to each other and different from all other known stars. And one of them comes from a type 1a supernova remnant. There's a whole host of things that we need to do, but since I've run out of time, I will just leave them as text and end now, sorry.
So the next speaker is Joshua Shaw. He will talk about the evolution of competing upstream neon white dwarfs.
All right, so I'd like to tell you about some work that my collaborators and I have been doing to understand how oxygen neon white dwarfs evolve as they grow. And oxygen neon white dwarfs are already born with relatively high masses, like 1.1 to 1.2 solar masses. But in cases in which they're accreting, they can go ahead and grow up to the Chandrasekhar mass. And it was kind of understood from stellar evolution calculations and hydrodynamic simulations, largely in 1D done in the 80s and the 90s, that when those oxygen neon white dwarfs grow to near Chandrasekhar, they collapse and form a neutron star. And that process is often referred to as accretion-induced collapse. And accretion-induced collapse is one of those things that's kind of long been predicted and hasn't really unambiguously been observed. The predicted signatures are relatively faint and fast, so maybe one shouldn't lose too much sleep about that, though if that continues into 10 years of transient surveys, you should probably get pretty nervous. There's some neutron stars that are well explained to be produced by this process, kind of young neutron stars and old populations like globular clusters. We'd really like to understand a little more about how this happens. And again, the way you get a system like this is actually very analogous to some of the kind of classical super Chandrasekhar mass type 1a scenarios that Kim just mentioned, except that instead of having a carbon-oxygen white dwarf, you have an oxygen neon white dwarf. So you have an oxygen neon white dwarf that's growing because it's accreting from a hydrogen-rich or helium-rich donor, or potentially you have kind of a double degenerate scenario where the white dwarf grows because you just dumped another white dwarf on top of it. And something that's really then developed only in the last couple of years is people have started doing multi-dimensional hydrodynamic simulations of the onset of the collapse of these white dwarfs. And it's been rather interesting because the idea that, oh, these things definitely collapse to form neutron stars has started to come into question. So some multi-dimensional simulations by Kendemoto and Xingqi Lung showed that some models of theirs exploded and some collapsed when they just were varying parameters. It seemed like they're well within the uncertainties of the initial conditions. And some calculations by Sam Jones and his collaborators found that many of their models, in fact, exploded and they didn't collapse to a neutron star. They did leave behind a remnant, and that remnant was some relatively low mass thing that is essentially a peculiar white dwarf. So some object, 0.3 or 1 solar mass that has actually quite an unusual composition. And so I think there's a real open question. People have been finding white dwarfs, low mass white dwarfs with weird compositions. Are these things connected to this? Is AIC connected to that process? And that's a question that we'd kind of like to answer and better understand. And one of the ways that I think needs to happen to push that forward is we need to better understand the kind of progenitor models for this process. So what are the oxygen neon white dwarfs like as they're going up towards collapse? And there's been a fair amount of work by myself and others pushing forward the modeling of this in stellar evolution codes, making sure that the reaction rates and other microphysics is being treated consistently so that we can really kind of get the best quality progenitor models that we have. And then I think it's also really important, and I'll say, I kind of try to explain why, that the composition of the initial models really comes from stellar calculations of super AGB stars, which are the progenitors of these oxygen neon white dwarfs. And we ought to be able to predict what are their compositions, and then we want to make sure that we can kind of use those compositions in the modeling kind of self-consistently. And that's something that people have been pushing forward, that is using oxygen neon white dwarf models from super AGB star models. And there were just a couple of papers on the archive, I think more or less in preparation for this meeting, of people talking about doing just that in terms of kind of cooling models for oxygen neon white dwarfs. So now I kind of want to give you a tour of why is the composition important. And so to do that, I'm going to show kind of the temperature and density space the material in the white dwarf is going to go through on its way up towards collapse. Okay, so we're talking about quite high densities. These white dwarfs are approaching Chandrasekhar, and some temperatures here kind of consistent with what we expect the central temperatures to be after the mix of neutrino cooling and compressional heating from accretion has set their evolution. So first I'll draw a set of lines associated with electron captures on magnesium-24 and neon-20, which again are important isotopes in these oxygen neon white dwarfs. And so if material gets to these temperatures and densities, we'll have electron capture reactions on these isotopes, and those are going to heat the plasma. They're going to heat the material. There's also a somewhat lower density on isotopes like sodium-23, which is also actually pretty abundant in oxygen neon white dwarfs, despite the name. You also have cooling due to electron captures that happens at somewhat lower densities. And then I'll draw a third set of lines associated with carbon burning. So you may, in fact, have some carbon-12 left over in your oxygen neon white dwarf. And where that carbon starts burning depends a fair amount on the carbon abundance. So I've drawn a whole set of lines. If you have lots of carbon, you burn at relatively lower temperatures. If you have only a small amount of carbon, you have to get hotter to really get the carbon fusion going. But because you have this whole mix of processes, heating over here, cooling over here, and carbon burning, kind of what's going to happen to your white dwarf really depends on the composition, and then what fraction of the material is these isotopes versus these isotopes versus these isotopes. And so you want to do your best to model that. So to do that, we've run some kind of super AGB star models with the MESA stellar evolution code. And I'm comparing those to some other super AGB star models in the literature. Here is a set from LCS shown in squares. And what's shown is, again, the kind of initial mass of the star versus the central carbon-12 mass fraction left over at the end of carbon burning. And you can see there's actually a huge range of carbon mass fractions. At kind of the lower mass end, you may have carbon mass fractions of a few percent or 10%, and even in some cases left. Whereas at the more massive end, you might have 0.1%. So there's a huge range. And MESA models with a kind of a variety of assumptions about rotation and mixing are shown in these symbols. Things move around because as you change your assumptions about rotation and mixing, you're changing the initial final mass relation. So things are moving around on the x-axis, so I wouldn't pay too much attention to that. But again, we see pretty similar trends on the y-axis, which is decreasing amount of carbon with increasing mass and a pretty wide range of carbon abundances in the models. And going forward, so you form your oxygen neon white dwarf, and then as you let it cool, it mixes. And this plot shows basically snapshots of the carbon abundance profile as a function of time at a variety of times, kind of roughly spaced logarithmically in time. And right after you form the white dwarf, sometimes the carbon profiles are quite complex. Exactly what these look like and what the variation looks like actually depends a lot on your assumptions about convective overshooting and other mixing processes. But the nice thing is if you wait 1 million years or 10 million years, basically the whole core mixes out and it's just homogeneous. And so it actually makes sense to say something like, this white dwarf has a carbon fraction of blah. And you can definitely give me 1 million years or 10 million years or 100 million years because I have to grow the white dwarf up to Chandrasekhar. It formed at 1.1 or so. So there's going to be some time elapsed between formation and collapse. So now we kind of had the warm up earlier of all these different reactions that can happen in density and temperature. And now I'll show you a couple of evolutionary tracks of white dwarfs going through this. So now I'm really showing the central density of a white dwarf model. It's accreting, so central density is really a proxy for time. So as the central density is increasing, time's going this way. And I show models with two different carbon fractions, one with kind of 1% and one with sort of 3%. So I start here, off I'm going. I get to these isotopes here where I have this Urca process cooling and my temperature really falls. And one thing that means is that I really can't hit the carbon ignition lines over here at very low density, at say 10 to the 9 grams per cc. There's been some reports in the literature of people saying, oh, you can get very low density carbon ignitions in these systems. But including these isotopes and including this cooling means you really get quite cold. And so you avoid hitting the carbon ignition lines here. But you go along a little further and you get to the first kind of heating electron captures on magnesium-24, and whoosh, your model goes up and starts getting quite hot. In the case in which there's kind of only 1% of carbon, this model shows, for instance, that, okay, there's a little bit of heating, but things keep on going, and I finally get to this point where I start oxygen burning, and I'm kind of getting close to collapse at a density of almost 10 to the 10 grams per cc, versus with this higher carbon fraction model, actually the carbon provides enough energy to get me up to oxygen burning right around here at a significantly lower density. And if you go back to the models and kind of the understanding, at least heuristically, and you look at where's kind of the critical density for explosion versus collapse, it's like something maybe around here, in which case, one of these models might explode and one of these models might collapse. And we've kind of only varied the carbon fraction by a small fraction and within the kind of realistic range. So there are still some uncertainties in these models, and in particular, some work I did last year showed that when you kind of do have these electron capture reactions in a pretty cold medium, you tend to become convectively unstable. And that's even in the absence of carbon. And when you have carbon burning triggered by these electron captures, it can get even worse. And your models become convectively unstable and want to start mixing. But once that starts, there's been long-standing challenges in understanding how stellar models that are convecting evolve in this regime because of the operation of the convective Urca process, which I don't have time to discuss in detail, but it does mean the kind of models that start mixing there still have standing theoretical uncertainties. All right, so I'd like to summarize and point out that I think one interesting thing that's developed in the last few years is that models are starting to kind of question whether oxygen neon white dwarfs that approach the Chandrasekhar mass actually collapse to neutron stars. I think there's a lot of interesting work that needs to be done and is being done to try to better understand the outcome of these systems. I think one important way to push this forward, which I've been doing, is trying to really model these systems and the progenitor systems as best you can. And part of that involves using models of oxygen neon white dwarfs that have realistic compositions. And finally, including realistic fractions of carbon in these systems, I think has shown that potentially the expected range of carbon abundance is perhaps enough to indicate that there's some diversity of outcome here. So it might in fact be that not all oxygen neon white dwarfs that reach Chandrasekhar have exactly the same fate. It may in fact depend on some of the details of their composition. Thank you.
Invite all the speakers to come up and have the questions. Anybody have a question?
Can I ask a question to Ken? I was wondering, did you also check for X-ray imaging or radio imaging to find supernova remnants?
Yes, on the X-rays, and we're working on the radio.
You didn't find any?
Oh, yeah, nothing in the X-rays. Well, sorry, so there is faint ROSAT emission for the one that's seen. I think it's faint enough that it'd be hard to see that on its own for the other ones, but it was looked for.
Okay. Also for Ken, you were positing that maybe they're fluffed up by some interaction with the supernova, but could they not just be low mass?
Yeah, so at their current radii, well, the current assumed radii, which looks like they're of order point few solar radii, they wouldn't be in a tight enough orbit to have gotten the orbital velocities they have, to be ejected with the velocities they have now. So they had to have been more compact than they are now.
For Josiah. So you were saying that some of these models are predicting that these oxygen neon white dwarfs could explode, but you didn't give any more information about what type of an explosion. Are these supernova type level explosions or what?
Yeah, I think this is, to be honest, somewhat unclear, but some of the explosion simulations look like either maybe low peculiar thermonuclear supernova explosions.
Okay.
For Stefan, the stars that you would identify as having been SDO or SD donors, so if you're looking for hypervelocity stars like that, do you expect them to continue to be hot subdwarf type stars after they've donated a lot of helium, possibly leading to a double detonation?
This double detonation scenario we are trying to prove is the actually single degenerate double detonation scenario, and so it's not a merger; it's a stable mass transfer, and we would expect the hot subdwarf to stay more or less intact. It might be a little bit more evolved already, so because you need some evolution going on before. And the lifetime of a hot subdwarf star on the horizontal branch is about 100 million years. So the lifetimes of those stars in these stages would be of the order of a few 10 million years before they turn into white dwarfs.
Stefan, do you think the coolest subdwarfs could also have hypervelocity?
You mean the SDAs, or? Well, why not? that depends on how you can do the double detonation. If you can do the double detonation with an unstable mass transfer, like Ken proposes, then you could do it with all kinds of helium whatsoever. That's how I understand it. And if not, if you need a stable mass transfer, then you are a little bit restricted. Then you need something that can stably accrete with the right proper mass accretion rate on the white dwarf. And then I think that narrows down your possible progenitors and ejected companions more.
So this is for Stefan. So the injection velocity of these stars are, I'm guessing, correlated with the mass of the white dwarf. So did you look into that? What kind of mass do we expect the white dwarf to have?
We did a rough estimate in our paper on US 708 about that. So of course, this is quite uncertain, but we would, when I remember correctly, more than one solar mass up to Chandrasekhar, and a binary period of about 10 minutes at the moment of the explosion. That's what we estimated. And of course, if we would find many more of those, it would be an interesting diagnostic to get to the explosion mass of the white dwarfs. And that's why it's also one driver to do that.
I just want to follow up on that because I think one of the most compelling lines of evidence that US 708 is connected is that its baseline I is similar to what you'd expect for something in about a 10-minute rotation, with about a 10-minute rotation period, right?
It's not, but it is it is if you assume that it evolved a little bit since then.
So I
Then
guess
it's good.
the follow-up to that is what's striking to me is that these things do appear to be rotating quite slowly. If they have been inflated, you'd expect them to slow down some. But I wonder if there's any inference you can make on how long you expect them to stay inflated, comparing US 708 to these other things that gets funny. That's not really a question, I guess.
I don't think that I have any feeling about that, how long they can be puffed up. Maybe Ken is better suited to understand.
In the conclusion slides that I didn't show, yeah, that's definitely one of the avenues of future work, is to figure out how to get the stars to where they are, and then the future evolution, how long do they sit there? Do they go back through where US 708 is, for example? Yeah.
All right, Steph, I have a question. Last question.
Yeah. I have a question to Ken. The D6 scenario, does it have any requirements in terms of metallicity? So can you do that in an old population as well, like in the Halo?
Yeah, I mean, there is some correlation between the age and the masses of the components that end up merging, but there's not like a metallicity issue, I don't think. I don't see why they wouldn't go off in the Halo.
Because then an interesting prediction of this scenario would be that you could have unbound hypervelocity stars that are falling, that are moving towards us from the halo,
right.
Which in most other hypervelocity scenarios you should not have. Everything else should move away from us. And if they are formed in the halo on one of those weird trajectories, they could just come back from nowhere and unbound. I think that would be an important, interesting observable.
Yeah. I think D6-1, I'm not exactly sure. I think the plot I showed, maybe that one is actually going towards the disk. Is that? Okay. I don't know. It's our paper. I don't actually remember, but don't you remember? No. So yeah, that's definitely true. The only issue is that there are fewer stars in the halo than there are in the disk, and so just by probability, maybe you get more things from the disk.
All right, that's it. All three speakers. So we will continue on type 1A progenitors. The next speaker is Alberto Masagas. So his title is What are the double degenerate progenitors in type 1A supernova?
Yeah. Okay. Okay. Okay.
The pointer and advance.
Perfect. Thanks. Okay.
Hi.
Okay. Well, this is a working that has been submitted in collaboration with Silvia Tunen, Valeria Corol, and Santi Torres. Okay, so the double degenerate supernova 1A, well, implies that we will have a merger within the Hubble time and with a total mass near the Chandrasekhar mass, okay? That's what you will call a double degenerate type 1A supernova progenitor, no? So there has been quite a lot of work in trying to find this kind of systems, no? And the success has not been extremely good, no? Except one system that appeared in a Nature paper that claimed that, not even in a double degenerate, but in a planetary nebula, and has been criticized. Apart from that, we have nothing. No? So the question of the main driver of this talk is to say, well, is this lack of observed double degenerate or double white dwarf supernova 1A progenitors a sufficient condition for disregarding the double degenerate channel or anything involving two white dwarfs for producing a type 1A supernova? So in order to answer this question, the idea was to simulate the double degenerate population in the galaxy and obtain synthetic spectra with the aim of identifying how many of these type 1A supernova progenitors will have double line spectra, because when you have double line spectra is when you can measure orbital periods and component masses, okay? So in order to do that, we needed to have a representative population of the double white dwarf binary population in the galaxy. And for that, we used the SEBA code in these two references. And this is basically some of the assumptions and typical prescriptions that you use in population synthesis models that I will not go one by one, but the most important here is basically this one at the end. No? The evolution of double white dwarfs is not entirely understood yet, but the best that we can do at the moment, unfortunately, is to use the alpha formalism or the gamma formalism, okay? And this is what we did here, okay? Apart from that, well, binary fractions, random distributions, as I said, yeah, typical assumptions that doesn't affect too much the final population. Okay, so there is, depending on the alpha formalism or the gamma formalism, in the entire population that contains around 370,000 double white dwarfs for the alpha formalism or 435,000, considering that we cut the population at 23 magnitudes, then there will be around 100 to 100 systems which will be direct type 1 supernova progenitors. And here what I call direct is those systems that will have a total mass of 1.3 solar mass or above and merging within the Hubble time. This will be the same, but for systems that do not merge, okay? And these ones will be the subpopulation of system of double binaries that would produce sub-Chandrasekhar explosions. And the same for the non-mergers. So we have 4 populations, direct mergers that will produce direct progenitors of the supernova, and basically the typical Chandrasekhar supernova and the sub-Chandrasekhar ones. Okay, so this is how they look like in the mass 1 compared to mass 2, where mass 1 is the first one that is formed, and in gray will be the typical Chandrasekhar supernova progenitors, and in black the sub-Chandra supernova progenitors, which in this case are a subsample of the entire, basically, Chandrasekhar progenitors. Okay. Those will be for alpha formalism, which I don't show the gamma alpha because it's very similar. And these are the temperatures. And these are the masses and temperatures again, but for the non-merger systems. So there are obviously many more systems that will not merge within the Hubble time. Okay. And here are the distributions. Okay, so these are the G magnitudes. As we said, there is a cut at 23 magnitudes. The orbital period distributions. These will be the direct progenitors. So those that merge within the Hubble time. That's why we have very short orbital periods. And these ones will be the ones that do not merge within the Hubble time, which allows a much larger orbital periods. And that will be the distances. So we can clearly see already that the population of supernova progenitors is intrinsically quite faint. So if you remember the motivation is if it's going to be difficult to find them or not, then with this we can start getting an idea of what we are going to find. So now that we have the population, it's fairly simple by knowing the effective temperature, the mass, the radius, the surface gravity from this population synthesis, and also the inclination, the period, and the distance, to obtain the synthetic spectrum for each component. And this is shown here for 2 different examples. So in gray, these are obtained interpolating in the model of a model atmosphere of Tetla cluster. You can get the two white dwarf synthetic spectra, but basically you sum up the fluxes and you get the final one. And this is assuming to the H alpha region because, as I said, I'm motivated in finding double line systems because not only I want to measure the orbital periods, but also the component masses. Okay, and that will be 2 different systems with these masses and effective temperatures, and in this case, a particularly high inclination. No, so if I go to a telescope and I get this spectrum, then I will be able to identify these systems as type 1 supernova progenitors. But the obvious issue here is that these are ideal spectra, so you need to incorporate the signal and consider the noise, and also to reduce basically the resolution. So what will happen if you go to a real telescope? No, this is what I'm trying to do here. Basically, I chose 5 different telescopes of a spectral combination that get a wide range in telescope apertures and spectral resolutions. I mean, you can add here whatever you want, but these 5 are quite representative in terms of resolutions, as you can see, and the apertures. And then you go to the website, and for typical observing conditions, 1 scene, 1 second of scene and gray time, and assuming 10 minutes exposure, I will tell you why 10 minutes, then you get this kind of relations, not the black points in the typical shooter websites, and then you just fit it. So if you have the G magnitude, you get the signal of your system. Why 10 minutes? Because as we saw, the orbital period distributions were very short, so you cannot really expose much more than 10 minutes. Imagine you are observing 30 minutes the system, then you will get orbital smearing. Okay, so you must be fixed. I mean, you can obviously increment the exposure time for the non-mergers, but because you don't know at the beginning of your observations what you are going to find, we are going to fix the exposures at 10 minutes. So that will be a few examples of what you will get observing 4 systems with these 5 combinations of telescopes and spectrometers. At the top left, I showed the ideal spectra. And then here in the other panels, I show how the spectra will look like in real, if they were observed by these telescopes. So in this case, you will be able to identify the double-line systems in pretty much all the telescopes, except in this one, in the GTC, because the resolution is too low. In this case, because the rate inclination is quite high, you will not be able to detect it in these telescopes, because this system is actually intrinsically too faint. But interesting, you will find it in the GTC. This is something unexpected I didn't expect. And then, well, here you have another example where you will find this system in the Magellan mic and the VLTF shooter, even in the GTC, and in this instance that you will basically not find anything. So you do this for all the population of systems. There's 100 progenitors, 100 to 100 direct supernova progenitors, and the 14,000, 20,000 of systems. And what you find is for the different common number of formalisms and for the different telescopes, what you will be able to find. So it's very little. Okay. If you go to the VLT-UVES, which will be the worst combination, you will find very few of them. Okay. And it turns out that the best combination, if you want to find double-degenerate progenitors or double-line systems, will be the Magellan mic, where you will find the most of them, followed by the VLTF shooter. So with these systems, what you can do is to get an estimate of the probability for finding type 1 supernova progenitors, simply dividing these numbers by the total population. For doing this, you need to consider basically systems that will be unresolved, and this is the probabilities that you will get. Okay. So for the typical classical Chandrasekhar progenitors, you will get a probability of 10 to the minus 5, and for the non-merger ones, 10 to the minus 4. So still is a probability which is quite low. What can you think about in the future? Well, with the next generation of telescopes, 30-meter telescopes, what will happen? So we analyzed that, and to make the story short, this will increase basically 1 order of magnitude. So it's still very low. Not impossible, but if you go just 1 by 1, the probability will be very low. Another option of finding type 1 supergiant progenitors will be to go to eclipsing systems. This is an example of eclipsing double white dwarf binary. LSST will find around 1,000 eclipsing systems. This is based on the work by Valeria Korol, using the same numerical simulations. However, in order to detect and to measure the masses, you also need radial velocities. And it turns out that only 3 to 7 of these double degenerate eclipsing systems will be supernova progenitors, and they will be all too faint for finding. Okay, so this doesn't help neither. Fortunately, with LISA, the things will change. And this is again input from Valeria Corol work in 2017 and her contribution to this, to our work. So she claims that there will be around 10 to the 5 white dwarf binaries that will be identified from the LISA, from experiment. So this reflects how many of these detections will be star 1s supernova progenitors. You cannot include here the individual masses, but LISA will be able to measure the chip masses and the orbital period. So these are systems in color for the different error in chip masses, and here will be systems above basically above this line that will be the progenitors. So you can clearly see from these pictures, and independently of the alpha or gamma alpha simulations, that LISA will be able to identify star 1s supernova progenitors. Okay, so these are systems with 30% error. This is 1% error and 0.1% error. So the conclusions: the probability for finding star 1s supernovas based simply on the double-line profiles is very low. Okay. Therefore, not finding double-degenerate supernova progenitors is not a sufficient condition for ruling out double-degenerate channels or subchandler channels. The next generation of telescopes, larger white-dwarf samples, or eclipsing binaries will not solve the problem. Fortunately, the gravitational waves detected by LISA will provide the much-needed input for testing the importance of double white dwarfs in producing double supernova. Thank you. Thank you very much.
Next speaker of the session is Thomas Kupfer. He will talk about high mass white dwarf and present examples in supernova finding.
Thanks. Okay. Okay. Yeah. Okay. Yeah. Thank you very much. My name is Thomas, and I already got a very nice introduction by Stefan and Kevin. Very nice. This saves me at least 20 minutes, so that's great. I might finish on time. So I'm to find systems like US708. You need pretenders for them, and you need binaries where you have a white dwarf, a massive white dwarf, which is able to blow up, with a helium star donor, and you have to make a helium star in an orbit that the helium star is still burning helium when it started accreting. So you need to start off after the common envelope with a very tight binary already. So the question was, do systems like this exist? And a few years ago, Stefan found CD-30. CD-30 turned out to be a well-known subdwarf with 12 magnitudes, so very bright, but not known as a very tight binary. But it turned out that this is actually a 70-minute binary. They found it by accident by just taking a few spectra and seeing that this, within a few minutes, was shifting quite a bit, quite a lot. And then follow-up photometry and then everything putting together showed that this is actually a massive white dwarf, or a fairly massive white dwarf, with a hot subdwarf companion in a 70-minute period, and it will get into contact in about 40 million years, while the SDB is still burning helium. And the theorists tell us that this white dwarf will most likely blow up. And the question is this a unique source? It's as we know now from Gaia, it's at a distance of only 300 parsecs, so it's really close by, or is this just a lucky coincidence? And that's something we try to do a little more systematic, to find more of those systems and do a much better search. Well, in the past, things like this were found by radio velocity shifts. So MUCHFAST, for example, was a survey which looked for SDSS spectra and looked for radio velocity shifts between those, and then looked for large velocity shifts. The problem is spectroscopy is expensive. You should do photometry. It's much easier, you can cover a much larger sky, because you see that these systems, because the SDB is already deformed by the white dwarf, you see that these systems show photometric variability, and that's what we were trying to do, look for photometric variability. So I went to a conference a few years ago, and there was a presentation on Omega White. Omega White is actually a very nice survey covering the bulge, where they do like continuous photometry for 2 hours to search for short period variability, and they presented this object, which is a very blue source. You see U minus G is minus 1. It showed a 22-minute period And in the paper, they say, oh, that's perhaps a pulsating subdwarf. Well, we all know that subdwarfs, they usually do not pulsate at 22 minutes. So we became a little bit suspicious and said, well, let's have a closer look. So I had a night on KEC on Iris, and I took a spectrum, 5-minute exposure, and I took another spectrum, and I saw a shift of 200 kilometers a second within 10 minutes. I was clear that this is not a pulsator. This is actually a binary. We wrote tons of proposals to Gemini, KEC, and so on, and they got more time and got more data, and it turns out that this is actually a 44-minute binary star. You see the Gemini light curve with the fit. You see the radial velocity curve right here. And it turns out that this is actually the most common compact subdwarf star with a white dwarf companion as we know of today. We did all the analysis. The temperature and the surface gravity is very typical for an SDO type star. The mass of the white dwarf turns out to be, again, relatively high. However, the subdwarf O star is lower than we would predict, right? So usually these subdwarfs, they have 0.5. That was a little bit, unexpected. It's a pretty low mass subdwarf O star. So we said, I asked my MESA friends to see, well, can we make sense of that? So we tried first a helium star model, like a helium core burning star, as you would expect for most of these subdwarfs. And it turns out that it's not consistent. You can only fit with a 0.47 solar mass SDB star, SDO star, and it doesn't work. On the other hand, if you say, well, that's not a helium core burning star, but it is actually helium white dwarf, you actually can do it, right? So we can, these are the overplotted models, MESA models. Here's the position of the star, and you see it's consistent with a 0.32 solar mass helium white dwarf. So we think actually the system is not a helium core burning star with a massive white dwarf, but rather a helium white dwarf with a massive white dwarf. What will happen in the future, we don't know. When it gets into contact, it will the contraction of the subdwarf will probably be faster than the orbital decay, so it will get into contact when it reaches a 5-minute period. All right, so omega white only covers a small area of the sky. If you want to do this more systematic, you go to try to cover as much area as possible. And as I used to be at Caltech and being part of the Palomar Transient Factory, we had this beautiful survey which was running for 8 years, covering a large fraction of the northern hemisphere. You see that's the sky, that's the southern hemisphere, that's the northern hemisphere, and PTF covered a large fraction over many years in the northern hemisphere with beautiful time domain data. We even also, the last 2 years of the survey, covered a part of the plane. So we had a look, and really, really quickly, we found a system at a period of 87 minutes. You see that's the PTF light curve. It's 2 orbits, so you see tidal deformation. It's a 5% variability. We took spectra. This is the radial velocity curve, and it turns out that this is a subdwarf, much more normal mass, with a white dwarf companion. But the white dwarf in this case is not. It's more like an average mass or low mass white dwarf companion, and the period is rather long with 87 minutes. So this white dwarf is certainly not massive enough to blow up when they go into contact. But we were encouraged. I mean, PTF shows that you can really do that. And we looked a little bit deeper and we searched more, and we found 2 more. So these are much more like typical numbers for what CD minus 30 is, 72-minute period, 76-minute period. So they will certainly still burn helium when they go into contact. This is the Chimera follow-up light curve. This is here again tidal deformation. Here the other system tidal deformation, the radial velocity here. And you also see that both of them are spun up significantly. So the rotation velocity is very large, it's above 100. And the semi-amplitude is also very large. And if you just assume a run-of-the-mill hot subdwarf, which is consistent with the temperature and the surface gravity, you get actually a minimum companion mass of 0.6 or even above 0.7. So this is more like the systems we are looking for. The analysis is still ongoing. We still do the light curve modeling, but this is basically very encouraging that there are more. And even more recently, we found a number 4. This is another system. It's again in a longer period, but the variability is very strong and very clearly visible here. The subdwarf is again a run of like a very typical subdwarf star. We only have a few spectra analysis. So the delta V at this point is like more than 450. I covered the orbit last week, well, actually 4 days ago with ESI, but the analysis is still going on. But These are now 3 new systems which we found. And something I would like to point out here, look, this is actually the galactic latitude, 8, 9, 13. And that's something we actually saw if you put them now on the galactic plane. All of these systems, all of these very, very compact white dwarf with hot subdwarf systems, all below an hour period or 90-minute period, they are all at low galactic latitudes, right? So CD-30 is actually the one which is highest off the plane, but it's also only in a distance of 300 parsecs. So that's, even though it's a little bit off, it's still a plane object. The question is this just because of stellar density, or is this really something that they are a young population and more towards the plane? Because the white dwarfs, except for this system, are usually believed to be more massive. And I'm looking here at the theorists in the room to tell me what this is, right? So PTF itself had only a little bit of a coverage in the plane. The plane coverage was there, but was not great. What you really want to do is do this much, much deeper, much, much more systematic in the galactic plane. And the plane is large, so you need a large camera to do that in a lifetime of a postdoc. That's why I'm part of the CTF, the Strictly Transient Facility. And here you see the sizes of the camera. So that's PTF. It's the size of the moon as a comparison. These are other surveys. And that is the CTF camera. Kevin showed this already. I think this is very impressive. If you are not impressed, this is actually on the sky, right? This is the Orion constellation, right? So you see that's the Orion arm. That's the size of the camera. And if you're still not impressed, let me show you the first light image. Probably have to turn off the light to see it nice, but anyway, so this is the first light image. This is the Orion belt. You see that's the M42 Orion Nebula. That's the Horsehead Nebula. And that's one, basically, 47 square degree field of view. So with that size, you can actually cover the entire sky, entire visible sky in one night, right? I mean, we don't want to cover the entire sky in one night, but we want to cover the plane, right? So we have now a survey with CTF to cover the entire galactic plane in a reasonable amount of time. And we have actually 2 survey types. One I call the fast and the furious, which is actually, the idea is you go to a field and you stay on this field and you take consecutive 40-second exposure for 2 to 3 hours. That should give you everything which is periodic on a period smaller than like 3 hours or so, right? So all these 1 hour, 90-minute period systems should fall out there, right? Because you don't need to come back like once and then you come back another night and another night. You just stay there for 2 to 3 hours. The other survey we are doing is a regular monitoring of the galactic plane, where we do 2 epochs each night. So that's G, 1 in G and 1 in R. And that's actually also part of the public survey. So the alerts, the transients happening in this area are already released. You can have a look and download them. And the photometry will be released on a semester basis. So the first release will be early next year. And this will definitely be a legacy survey, a legacy variability survey for covering the entire northern galactic plane. And we have started already a few weeks ago. And like a very, very early proof of concept is this system. It's a 5-minute SDB pulsator, right? So we can find very, very short period variability in this kind of survey. So to sum up, since the discovery of CD-30, we actually discovered 5 more compact subdwarf, hot subdwarfs with white dwarfs. OWJ0741 is the most compact with a period of 44 minutes. It's most likely consisting not of a helium core burning star, but of a helium white dwarf with a massive white dwarf companion. And I think something interesting is that all of these systems are located at low galactic latitudes. And in the near future, the CTF Galactic Plane Survey will most likely uncover more and allows us to do this in a much more systematic way. And we expect many, many more new discoveries in this fantastic data set. Thank you very much.
Okay, we have the last speaker of the session, is Robert Fisher. So he will talk about detonation, initiation in turbulent electron degenerate white dwarf methods.
Thank you very much. So it's my pleasure to be here today and to tell you about some research I've been doing with my students, my former student Pritam Mozumdar and my current student Gabriel Casabona, about detonation initiation. But before I talk about that, I wanted to remember our great colleague Enrique, who we are working on one project on oxygen, neon carbon oxygen mergers, just the week of the tragedy. So in fact, on the Wednesday before the Saturday of his accident, we're still exchanging emails talking about this work. We've heard several moving tributes to the great legacy that Enrique has had on the field. And one of the great things about the last year that has emerged is Enrique's continued to live on. A number of papers have been published this year with Enrique as a co-author. And so I thought, as part of that legacy, I'll be presenting a poster on this work that we're working on oxygen, neon carbon oxygen mergers, which leads to a very faint transient. And so this will be in a poster session. And if anyone wants to come by and talk about that and reminisce about Enrique, I would love to. The main topic of the talk is something that we're actually, with Enrique, we're planning to do this work just last summer. We're just beginning the stages of this, and to talk about the central problem of the type 1a field, which is really, when you think about all the different mechanisms, the different channels that lead to type 1As, we have the single degenerate channel that we've heard about today, the double degenerate, the double detonation in the D6 scenario that Ken Shen has talked about, and also the double degenerate channel. They're all very different channels. They have different progenitors. They lead to possibly different outcomes. But what's one thing they all have in common? They all share the problem of detonation. And detonation initiation is central to the entire problem of the type 1A, and it's not very well understood. So I want to talk about that today. First off, there's a couple of ways you can initiate a detonation, and there's a classic way that was originally proposed by Zeldovich. So let me just really briefly explain to you how that works. The idea is very simple. Let's suppose you have a very hot region of a degenerate plasma, heated up to around 2 × 10⁹ Kelvin. And so we see this kind of temperature ramp that exists. There's a little ramp above the temperature background. Here it's around 10⁷ is the temperature of the background. It's not exactly 0, but it's very cold relative to 2 × 10⁹. And here's the carbon-oxygen abundance. The carbon abundance is about half initially. So what will happen is the carbon will start to burn. There's a subsonic flame that gets propagated through this medium, and it sends out a shock wave in front of it. Now, I'll show you this is a frame from this in the movie. I'll show you in just a second. The burning front you'll see is where the carbon abundance drops off, and then the shock front is where the temperature spikes up. And in successful detonation, these two fronts propagate together, accelerate down the ramp, and the success is a successful detonation. The result is a successful detonation. So it looks something like this. Shown as a movie, you get this front, the two fronts propagating, and then the successful detonation coming out of this. That's the standard lore of how a detonation is initiated. But we've learned a lot about type 1As over the last several decades, especially the last decade, with new mechanisms being proposed beyond just the standard classical single degenerate Chandrasekhar mass explosion. So what does that have to say? What do those channels have to say about the detonation initiation mechanism itself? Well, let's take a look at that. So the Zeldovich mechanism makes several key assumptions, one of which is that the flow is laminar. You know, the flame is just a laminar flame burning on this quiescent background. The second one is that the burning occurs in the flamelet regime, which is almost saying the same thing in a slightly different way, that the flame is a real flamelet, and whatever kind of flow is in the background, if there's some turbulence, doesn't break up the flame. The third one is that the heating is provided by nuclear energy. The nuclear burning is dominant. Well, what do the modern mechanisms have to say about this? Well, the laminar flow, here's the D6 simulation that Ken was talking about earlier that James did a number of years ago, the earliest stages of this, you see the helium being accreted onto the white dwarf primary over here, and you can see the flow is highly turbulent, right? It's not a laminar flow at all. The Reynolds numbers are like 10 to the 16. So it's highly, highly turbulent conditions that lead to detonation. Okay, so it's not a laminar flow at all. The flow is turbulent. Well, what else can we say? One property of turbulence is that you get this cascade of eddies that goes down to small scales, right? And those small scales can disrupt the flame. What does it look like? It looks something like this. This is my little cartoon of what this would look like. Here's one turbulent eddy. Here's the flame surface over here. And when the velocity of that turbulent eddy becomes comparable to the flame surface, that turbulent eddy can start to disrupt the flame. The number that characterizes this is called the Karlovitz number. So if you have the smallest scale eddy being inside the flame itself, Karlovitz number is 1. Okay? If the Karlovitz number becomes very large, it means turbulence can actually disrupt the flame itself. What do these channels predict? Well, Karlovitz numbers is like 10 to the 3 or 10 to the 4 in the double degenerate or the D6 scenario. What does that mean? It means the flame is completely disrupted. It's not laminar at all. So we're in what's called the distributed burning regime, which means the flame is completely disrupted, which is very different than what the Zeldovich mechanism talks about. The last one, the last assumption being nuclear energy is dominant, well, that too, if you have a very strong source of turbulence, then actually turbulence is actually at lower temperatures very much more important than nuclear heating. So that's shown in this plot here. If you take a gas which is at 2 times 10 to the 9 or hotter, then carbon burning is more important than this very strong source of turbulence in these channels. At lower temperatures than that, the ratio, what's shown here is the ratio of nuclear to turbulent dissipation, the turbulent energy is more important by many orders of magnitude. This is just another way of saying that because the carbon burning rate is so sensitive to temperature, you don't have to turn the temperature down very much before other sources of heating, in this case turbulence, becomes much more important. So the last point here is that actually below a temperature around 2 times 10 to the 9, which is, by the way, the kind of temperatures that come out of these simulations is around 10 to the 8 to 10 to the 9, it's not the nuclear source of energy that's most important, it's the turbulence, sometimes by many orders of magnitude. So what does this say? It says that in double degenerate mergers, detonation is initiated in this distributed burning regime where turbulence is most important. That's completely different than the classical Chandrasekhar mass picture where the flame begins as a flamelet. And the question then arises is how does a detonation actually initiate in this more realistic scenario? So let me show you a cartoon of what this looks like before I show the simulation. So here's a little cartoon. Here are a bunch of turbulent eddies. This is the turbulent cascade represented pictorially inside an electron degenerate plasma. So turbulence dissipates, which means turbulent eddies will disappear. They get dissipated into heat. They heat up the plasma. Those are eddies where the characteristic turnover time is shorter than the characteristic nuclear burning time. But what will happen is, as these eddies dissipate, they inject more energy into the flow, and the flow gets more energy propagated down through the cascade. They heat up the plasma. That's what's going on. And one eddy, eventually, of a critical size, has enough temperature in it that its characteristic burning time is shorter than the eddy turnover time, heats up, and will cause a detonation. So that's the basic cartoon picture of how that detonation can be initiated. Does it work? Well, we've simulated this in 3 dimensions. Here's the sort of setup of the simulation. We drive a turbulent box of a scale which is much smaller than the white dwarf scale. It's essential if you're going to resolve the kind of characteristic scales that are important here. The box is all on 100 kilometers in extent. The density is around 10 to the 7, temperature is 10 to the 9, and the characteristic velocity is about 2,000 kilometers a second. This is the simulation itself. And what we're seeing here is the projection of the nuclear energy generation rate, and it's on a log scale. So let me just show the movie. So you'll see many, many eddies will develop. Most of those eddies, if you watch, they just get turbulently dissipated away. But there's this one eddy down here where eventually the temperature reaches the critical temperature around 2 × 10⁹, grows up and develops into a detonation front, which is a successful detonation. So that's a picture of how a realistic detonation arises. This is a slice through those two images of the same simulation shown through the hot spot at the center, in this case, of the temperature on the left and the burning rate on the right. And the key point to realize here is that the mean temperature on the left in this box is around 10⁹. The standard conventional Zeldovich mechanism would predict this would not detonate at that kind of detonation initiation temperature, but the burning rate with the presence of turbulence can be boosted by orders of magnitude. In this case, about 4 orders of magnitude above the mean. So let me just conclude very briefly. To summarize, the Zeldovich gradient mechanism makes several key assumptions, none of which are really valid in modern dynamical mechanisms of type 1As. The turbulent-driven detonation mechanism, which we discussed, boosts the burning rate by orders of magnitude and can initiate supersonic burning and a detonation. And it leads to a broader range of detonation initiation conditions than previously thought possible. And this has significant implications for dynamical merger mechanisms, including double degenerates, D6s, and even potentially for the classic single degenerate channel. Thank you very much.
All the speakers in this session, please come up. And now we have a joint question and answer session.
Yeah, the question to Alberto. This was a very interesting simulation you did. I'm wondering why haven't we done that before? Because it contains so much information. The other thing I would like to ask you, getting back to the CD-30 system that Thomas showed, when we did the follow-up of this system, we also got some follow-up from a small telescope from the Mercator. And because they had to integrate quite long for the star, the spectra were weird, and they look terrible. I've never seen such terrible spectra. And my question is, can we not use that maybe to look for a double line system, so the other way around? Because what we will have are these large area surveys where we have 20 minutes, half an hour integrations on lots of objects, and could one not use the simulations that you made it to maybe find a way to quantify the weirdness or the ugliness of a spectrum to see whether it's a weird binary?
I wouldn't know what to say. I guess it's probably possible to do, but I guess if it's too noisy, then you probably cannot get much information about it. If it's very broad and very noisy, maybe that will help. But if it's just simple noise, I think it's very difficult.
I think Thomas has a comment.
Can I just briefly comment on that? For the 20-minute system, which Kevin presented earlier today, we took in the beginning just identification spectra to see what it is, like people say or whatever. And we integrated very long. And to fit the data, we actually had to include a rotation velocity of about 1,000, roughly, something like that, about 1,000, which is obviously weird, as you say. So that might be a way of doing this.
Question by Ken.
Thomas, I know you've only seen a few of these sources, and obviously this is hard. Can you estimate a rough rate?
Not yet, no. But to be honest, I actually haven't thought about it yet. But okay, no.
Okay, so a question here in the back.
Just two comments. One concern in the these observations. What is important is that with LISA, we will be able to go quite far from the sun, from the sun. So in practical observation, we are only studying the local geopolitical methods. with Lisa, we will study a volume that is representative of the galaxy. I think that is important. The second question has to do with the hidden detonations in the outer layers. Remember that integral observations of supernova 2014J show a strong signal near the maximum due to the nickel 56. The interpretation is perhaps not doubtful, but challenging. But anyway, the signal is there. The best way to predict the signal is to have nickel 56 layers.
It's for me.
Well,
the Lisa plot that I showed is well, let's begin from the beginning. The numerical simulations show distributions up to G magnitude 23, but the Lisa simulations go to G magnitude 27, so it does include many more systems. That you will not detect electromagnetic, but with Lisa gravitational, yes, so it will go much further than that. For the other question, I'm not sure if I understand your comment, but here we are looking at progenitors, not the signs of the explosions already, but simply looking for progenitors themselves, just looking at double lines or eclipsing systems, or just to see if they exist, and then in the future they will merge and produce supernovae.
Sorry, my second comment was concerning to the physics of the future is very outdated.
But how should we take this into account with this kind of work to find the progenitors?
The second one was for Robert, not for you.
That's for Kim.
Yes. No, I agree. It's a great comment. There's that picture that in 2014 is a kind of belt of nickel 56. So that would potentially be a signature, and especially if you could see it in an early time light curve evolution. No, that's
it was very impressive numerical simulation. So my question is that direct numerical simulation, or are you using some turbulence upward model?
Yes. So the short answer is that doing a direct numerical simulation in the white dwarf context is almost impossible because of the Prandtl number being so incredibly low. However, in the distributed burning regime, the microphysics, namely the electron conduction and the viscosity, play minor roles. It's actually the turbulence that's playing most of the important role in transporting energy and momentum. But there is not an explicit subgrid model for the turbulence. It's what's treated in what's called an implicit LES approach. But we can talk about that more offline. We did convergence studies on it.
Hi. So my understanding is the double detonation scenarios, this is a question for everyone, actually, is that it doesn't require a stronger, safer, advanced white dwarf to detonate, right? So has any modeling been done to see if the light curves generated from this type of detonation matches the observations?
Yeah, the short answer is yes. Those are the papers. I don't know if Ken wants to comment on this, but I mean, basically the German group did early simulations of, that, and they showed that the light curves actually agree better than most other predictions.
Okay, one last question by Tom.
So for Alberto, I'm wondering about your number. I think it's 2 in 100,000 chance that there is actually one of the SPY white dwarfs that's essentially consistent with being a double degenerate in the sense of being greater than 1.4 solar masses and with a short enough period. It's just not proven in the sense it's just on the boundary. I think you were saying 1.3 or something, but that was 1,000 white dwarfs, so 200,000 doesn't sound as though it's necessarily right to me. Can you comment on that one?
No, it's
double line system.
Double line system from SPY.
Yeah.
I was mentioning some other found in a planetary nebula. Not that one. Okay. Well, but the one you mentioned is consistent with being, so it will merge within the Hubble time.
Yeah, it'll merge the Hubble. It's like 10 hours, I think, but it's just on the edge of it.
10 hours.
Yeah, so it will merge. It's 1.4 total mass, but it's got an error bar that will take it below 1.4 as well. But only a small error bar.
Okay.
So,
Well, that will be yeah, a per unit.
well, my main point was the number, right? Well, 1,000 systems, and your number was 200,000. So, it doesn't sound very likely you would have found such.
Well, the probability was simply the same. Okay, how many will be able to identify as supernova progenitors, and then we divide it by the total number of systems. That's a numerical simulation. Obviously, this can be different. You can run another simulation and find slightly different numbers of progenitors. That's why we take the
factor of 50.
Well, we were extremely lucky. I don't know.
All right, so we will continue discussion at a happy hour. So let's thank all speakers again.
Before we go, I have a few announcements. Number one, that's the one that Fab is probably going to say. If you are a speaker from tomorrow morning before coffee break, please send your talk to eurowd@gmail.com or talk to Fabi, please, by tonight. What time? What time do you go to? Okay.
Thank you.
Within an hour, okay. I can call you next year. Another announcement, if you are a member of the SOC, we're gonna meet at 6 o'clock in that flower over there. I don't have any other meeting points, so it's right there, okay? What else? Both, for both, SOC for IU and for the current one, we meet by the flower. The socks, okay? 6 o'clock, the socks. Both parties, 2 day reasonable hours